Alright folks, this week we're going to be talking about Newton's laws and one-dimensional forces. So you're going to find that there's some vocabulary attached which you guys should do some research and complete on your own, and then I'm going to guide you through the actual notes, which again you guys should either print. You can print a hard copy and just take notes with a pen or a pencil, or if you want to try to just follow along, and if you want to document the notes digitally, you can certainly feel free to do that. So we're going to talk about Newton's three laws. It's a pretty common concept. I'm sure you've probably heard about it sometime in the past. Newton's first law describes objects at rest staying at rest and objects in motion to stay in motion unless they're acted upon by some outside force. So this is also known as the law of inertia. So as we go through this, most of Newton's first law is somewhat comprehensive. It's somewhat of an idea or a concept as to how things move or don't move. There isn't necessarily a mathematical equation that goes along with it. Unlike Newton's second law and even some of the applications of Newton's third law, we can actually use a little math to prove it. So the first couple of examples basically say this. First one says an object is resting on a flat surface, and it asks, can the object ever start moving if the force never acts on the object? So if something's sitting stationary, no forces are ever going to act on it, no net forces are going to act on it anyways. You maybe have gravity pushing down and normal force pushing up, but no other force ever comes and acts on it. The question is asking, can this object ever move? Well, the simple answer to that is the big NO. It cannot move because there's no opposing force, there's no unbalanced force acting on it. If forces are balanced and they stay the same, the motion will not change. One misconception potentially about this is this object or example was motionless. It wasn't in motion to begin with. So of course if there was no added force, net force added to it, it cannot start moving. However, objects that are already in motion, and if the forces are, say, balanced or there is no net force, sometimes those objects can still be moving even though there's no net force, and they can move on forever and ever. So the example of that maybe isn't so much played out on the Earth or within our atmosphere, because we always have friction that we deal with. But if you take things to outer space where in essence things are frictionless, a little bit different. And example 2 kind of talks about that. So reading through example 2, it says there's a spaceship coasting through outer space. It's traveling at 20,000 meters per second away from any significant gravitational force. How fast would the object be if it was moving at 20,000 meters per second and it never came in contact with gravity or other friction, so no other net forces, and even if its engines are off, it's coasting, it has inertia, it just continues to keep moving, it's always going to be going at 20,000 meters per second. There's no way for it to slow down or speed up or change direction. Newton's second law, this is where we actually start to apply a little bit of mathematics. So there is a mathematical formula that goes at the basis of Newton's second law, and then we have to use some of the concepts of the first and second law when we go to solve problems involving Newton's second law, because we have to draw diagrams and find net forces and balancing forces and determining positive and negative forces and things like that. However, these are the basic things you need to know about Newton's second law. It states that the sum or the total of the force acting on an object is equal to the mass of the object multiplied by the acceleration of the object. Now, if an object doesn't accelerate, it means that there is no net force present. Again, that doesn't mean that if there's forces acting on an object that it has to be accelerating, because forces can be balanced, they can have a net force of 0. But if something does accelerate, that means there's a net force present. So if it's speeding up, slowing down, or changing direction, assuming that the speed stays the same, the direction is still a change in velocity, therefore an acceleration, a force must be present. So we'll do a couple of example problems. In example number 3, they're talking about a fighter jet being launched from rest. So it says an F-18 Hornet has a mass of 20,000 kilograms when fully loaded. Its afterburners are applied to both engines. It can accelerate from rest at a rate of 10 meters per second squared. How much force do the engines produce altogether? Well, just like when we solve any 3-variable equation or 4-variable equation, you want to follow the same process to solve. You want to list the variables, list the equation, and then solve. So for this, your variables are force, mass, and acceleration. So when I go to solve these problems, I'm going to list what is the force, what is the mass, what is the acceleration. And again, they're going to give you 2 of the unknowns. They're going to have 1 that will be an unknown that you need to actually solve for. So reading the problem, let's list the things that they do give us, and then we'll solve for the unknown. So they do tell us that the mass of the F-18 Hornet is 20,000 kilograms. So the units for this are appropriate, meaning we do not have to convert. If you were given a mass in grams or pounds or something like that, or milligrams, you'd have to convert it to kilograms in order to get a newton, because a newton is a kilogram meter per second squared. So the units do have to match up. So your base unit for mass when we're dealing with force is a kilogram. Let's look what else they give us. They do tell us that the airplane is able to accelerate at a rate of 10 meters per second squared, and acceleration, of course, is always in meters per second squared. It's a change in velocity divided by time, so you got meters per second divided by seconds, which will give you meters per second squared. The unknown here then would be force. What is the force? Well, referring to the base equation for force, equaling mass times acceleration, we don't really have to do any rearranging or solving. We just know we take the mass multiplied by the acceleration. So the numbers here work out quite easily. We're just taking the 20,000 kilograms multiplied by the 10 meters per second squared, and you're going to get 200,000 newtons. Variables. Rearranging this equation to solve for mass or acceleration will look something like this. If you're solving for mass, they must give you force and acceleration, which would be F divided by A. And if you're going to solve for acceleration, you're going to do force divided by mass. So some simple rearranging of the variables, and we have some more useful equations depending on our application. For example number 4, they say a speeding luggage cart is traveling too fast on the tarmac if the car and luggage has a mass of 29,000 kilograms and the brakes are applied, frictional force of 12,500 newtons to the car. What would be the rate of deceleration, which is just a negative acceleration? Follow the same steps, list the variable, list the equation, and solve. What is the acceleration? Pick the equation that they use to solve for acceleration. Acceleration is force divided by mass. Plug in the values. Divide and solve. And you should get 0.43 meters per second, 3 meters per second squared. And Newton's third law. This again does not have any mathematical equations necessarily, but it's more of a conceptual thing. It just basically states that forces act in pairs. It's impossible for a force to act unless it happens in kind of equal and opposite magnitude and direction. So it will say that for every action there's an equal and opposite reaction. There's many applications for this. So if you're orbiting around a planet, like the moon orbiting around the Earth pulls on the moon as much as the moon pulls on the Earth. Oftentimes it's misconceived that the larger object is always pulling on the smaller one, but there's always, to some extent, a small force of the smaller object acting on the large object. Just as if you or I were to jump up on the Earth and then get pulled back down to the Earth, yes, the Earth pulls you back down, but when you jump, you push the Earth down, and when you get pulled back down, you pull the Earth back up, just as much as you pushed off of the Earth and or gravity pulled you back down. It's equal and opposite. Now, are the differences in the force minute compared to, say, the inertia or the mass of the Earth? Absolutely. Thus why when you jump up and down, the Earth does not shake. Some examples for Newton's third law. Example 5, it says to draw a free body diagram of a block with a mass of 10 kilograms sitting motionless on the floor. Be sure to include your f of g and f of n. So, example 5 looks like this. A motionless box sitting on the ground. In the diagram, you can draw a simple box sitting on the ground. There's 10 kilograms of mass with this box, so if we want to label this as 10 kilograms, we can. And there's going to be two forces. Remember, there's no such thing as one force. Forces always act in pairs. So the one thing we do know is there's a force pushing down, and there's a force pushing up. The force pushing down is the force of gravity. This is what we call F of g. The force pushing up would be the equal and natural opposite force pushing upward, which we're going to call F of n. Now, the one thing that we do know is force of gravity is equal to mass times acceleration, just like any force would be. It's a mass times an acceleration. Our mass is given to us as 10 kilograms, but the acceleration of even stationary objects is the acceleration of gravity. It's pulling down at 9.8 meters per second squared. So if we wanted to solve to get a numeric value for f of g, we would have to do 10 kilograms multiplied by 9.8 meters per second squared. And if we multiply 10 by 9.8, you're going to get 98 newtons. Typically in a free body diagram, you want to note some direction as positive and some direction as negative, whatever is the opposite. You have the choice which direction, up or down or left and right, in each way that you want to be positive or negative. For simplicity reasons here, I'm going to just say that f of g is positive, and we'll say that f of n is negative. So I'm calling the downward force positive and the upward negative. You could very easily do it the other way. Quite common that they call a gravity a negative force pulling down and a positive force going up. I do not need to recalculate f of n. According to Newton's third law, forces act in pairs, they're equal and opposite. This object is in equilibrium, therefore the forces are balanced, so I can just simply state that f of n is equal to negative 98 newtons going in the opposite direction, which means the net force acting on this object is 0. So that's why there is no change in motion, there is no acceleration, and Newton's first law and second law are also satisfied or both happy. Example number 6 is going to talk about equal and opposite forces also, but maybe with something that's actually in motion, maybe a collision, things that are actually colliding with each other. So the example reads, a turbine blade on a A320 is spinning at a very fast rate during flight. A lost duck is on a destructive path with the intake. 12,000 newtons is applied to the duck during the inhalation. How much force is applied to the turbine blade? Well, we could draw a free body diagram for this, but they do not ask. It's simply, again, a conceptual question. If the duck flies in and gets smashed into the engine with 12,000 newtons of force, how much force does the engine apply to the duck or the duck apply to the engine, and vice versa? Well, if we say that the force applied to the duck is equal to 12,000 newtons, then we could also say that the force applied to the turbine or the engine, the turbine, is equal and opposite to what it is. In the table below, we're going to see a little bit about abbreviations and symbols, superscript, subscript abbreviations to get an idea of what we're talking about. So these are not all of the symbols we would see and use, but it's just to kind of give you an example of kind of how the concept or process works. So you'll see the force on the left-hand side, the type of force, whether it's frictional force, normal force, weight, or any other force. A person pushing or pulling on an object could be the force of a helicopter rotor, it could be a jet engine, it could be the wheels on an automobile, whatever. There's millions of examples we could list. The one thing you will see in common is they all start with a capital F, but then the lower subscript number, which is the small one to the right-hand side, that abbreviation normally identifies what type of force we're talking about. So F of F, which is very common, this is a force of friction of some sort. F of N is very commonly force normal or normal force, and F of G is weight or a gravitational force pulling down on an object. And those are probably some of the more common ones we'll use. Just talking about adamant objects like a box sliding down a ramp or being pulled across a desktop or something similar. Again, dependent on the application, we could list many, many others. Typically, the force of the other would be, some sort of an object or a person. Whatever is applying the force or the force is being applied to, potentially, and what direction, well, that's going to be described per problem or in the example diagram. Maybe somebody's pushing at 60 degrees from the horizontal, maybe they're pushing due east, or someone's paddling due south or falling straight down. Any of those could be considered a direction. Again, as we get further on and talk about two-dimensional motion, we'll be much more apt to being very specific on what direction something's pointed, either determining directions from like a bearing from degrees north on a 360-degree grid, or talking about degrees above or below the horizontal, or sometimes away from the vertical, either east or west from the vertical. All right, example 7 talks a little bit about how to draw and or summarize and label free body diagrams. So these are very basic, but the application will hold true for even more complex settings. So, in example number 1, it shows a block. It shows an arrow pointing to the left, an arrow pointing to the right. The one on the top says 3 newtons, the one on the bottom says 4. One thing that you're going to do when you sum up forces and try to find net forces is, in a diagram, you have to again determine what is positive and what is a negative direction. So that is totally up to you. I mean, a lot of times the problem, if you're reading a problem out of a book or online, or if I give you a quiz or a test, I'll have to tell you what direction is positive. Maybe down's positive, up's positive, or left or right. Either one's fine. So this picture does not show what way is positive. So I'm going to denote the right direction to be positive. So I'm going to say that I'll take a little arrow and point it to the right, and I'm going to call this as positive, and I'm going to call this as negative. So it'll look something like this. So now, when I go to sum up my forces, I know that the 3 is really a negative and the 4 is really a positive. So when I go to find the force net, you literally sum up the forces. We have 4 newtons minus 3 newtons, which means my net force is a positive 1 newton. Now, the sum force acting, or the net force acting on this block then, is really the same as just 1 newton. So if I wanted to figure out, say, the acceleration of it, I could have the mass, and maybe I know the force now. I could do the force divided by the mass to get the acceleration. So multiple forces don't do you any good until you sum them up or get the net force. Example number 2, this one has 3 forces acting on it. It doesn't matter if there's 2 or 3. We got to denote what direction is positive, so I'm just going to keep it the same, going to keep it consistent. I'm going to say the direction to the right is positive and the direction to the left is negative. So this is what it looks like. I have 2 forces going to the right and 1 force going to the left. So my 4 Newton force here is pushing that way as a positive. My 3 Newton force here is also a positive, and my 8 Newton force, which is going this way, is considered a negative. So I'm going to sum up the forces, find the force net. I have a positive 3, I have a positive 4, I have a negative 8. 3 plus 4 is 7, and 7 minus 8 gives me negative 1. So that means the net force acting on this block is 1 Newton negative, which would be 1 Newton to the left. For example 4, again there's three forces acting on the block. I'm going to consider to the right to be a positive force. I'm going to consider to the left to be a negative force. I have 2 forces going to the right, positive 3, positive 2. I got 1 force going to the left, which is negative, so I'm going to sum these forces up. Force net is equal to 3 newtons plus 2 newtons minus 5 newtons, which means that my net force for this is all going to cancel out, which means it's at 0 newtons. So that means that block is in equilibrium, or has a balanced forces acting on it, or a net force of 0. So this block, if it was not moving, would never move, and if it was already in motion, it would continue in motion at that same velocity. And then for number 5, again we got a force pulling down and a force going up. I'm going to call the upward force positive, I'll call the downward force negative. Do the net force. 7 minus 3, which gives me a positive 4 newtons, which means there would be 4 newtons pushing upward on this object, would be the resultant of it all. And example number 8, the very last one. So it shows a picture of a car. It's producing positive force in 2 different ways. If I call forward positive, I got a plus here and a plus here, and then in the back it's got one way it's producing a negative force. Now with this one, they take it just one step further. Not only are you going to find the net force, but you're also going to have to try to find what is the rate of acceleration for this object. So this is where the application comes in. Determining net force is great, but can we take Newton's second law and apply it? We're going to do it right here. So let's first find the net force. So the force net. I got a 10 newtons to the right, or a positive 10 newtons boost from the rocket on the back of the car. I got 10 newtons going to the right, which is a positive force produced by the wheels or the engine in the car. So I have a 10 newton plus a 10 newton. So right now I'm in the positive 20 newton as a sum. However, there's a parachute out the back of the car, which is a negative force. So this is going to be a minus 7 newtons. So I have 20 minus 7, which is going to give me a force net equal to 13 newtons. Now, they want us to find the acceleration, so go back and look at Newton's second law. We know that acceleration is equal to force divided by mass. Whenever you plug something into Newton's second law, you don't want to do just one single force unless it's already been summed up. For example, on the car, there's 3 forces acting here. We would not want to do force divided by mass, force divided by mass, force divided by mass, get 3 accelerations, go through all this work. Nope, you want to find the net force divided by the total mass of the car. So that's what we got. We got 13 newtons. We got a total mass here of 10 kilograms. Again, newtons and kilograms, acceleration in meters per second squared is all of our base units for acceleration, force, and mass. Therefore, we're going to get 1.3 meters per second squared. That would be the acceleration. Thank you very much.
Force.